Every year, our cities seem to lose more ground to the weather. Concrete cracks, steel bridges rust, and increasingly, we find ourselves wading through our own streets after a routine storm. Our usual instinct is to look forward. We assume these challenges require 21st century fixes, expensive sensors, massive municipal budgets, and synthetic materials developed in a modern lab. 4,000 years ago, engineers on the Indian subcontinent were facing these exact same threats: extreme droughts, heavy monsoons, and the relentless wear of time. By mastering the mechanics of water, stone, and steel, they built systems that stood for centuries. Today, modern civil engineers are returning to those ancient sites to study the specific techniques that made them last. Around 2500 BCE, the Indus Valley civilization supported massive population centers. Harappa and Mohenjo-daro were highly organized megacities designed to accommodate thousands of residents in a dense, permanent environment. These cities were mapped out before the first brick was laid. Residential and administrative zones snapped to a rigid, mathematical grid, with straight streets intersecting at 90-degree angles. To execute this plan, builders mass-produced fired bricks. By baking the clay at high temperatures instead of drying it in the sun, they created a standardized, water-resistant building material that allowed for rapid, uniform construction. This standardization supported an unprecedented focus on public health. The builders engineered the entire city structure to safely contain and manage water. Nearly every private home featured its own bathing area and latrine, which fed directly into a network of covered, underground terracotta drains running beneath the streets. It was a centralized sewer system operating thousands of years before the industrial era. They even scaled this up to the public level, waterproofing large municipal structures with natural tar to create communal bathing tanks that could maintain hygiene for thousands of people without leaking into the surrounding soil. While modern urban planners often treat deep sanitation as a recent innovation, the builders of the Indus Valley proved these systems are the foundational requirements for a functional city. Moving south into regions like Rajasthan and Gujarat, ancient populations faced a different challenge. Here, the landscape alternates between punishing droughts and intense seasonal monsoons. Water is the primary limit on survival. To manage this volatility, engineers dug into the earth to create a bali or stepwell. Sites like the Chand Bowery are massive, inverted pyramids carved down to the water table. The geometry is practical. During the heavy monsoon rains, the wide, open mouth of the well harvests millions of gallons of water. As water levels dropped during the dry season, the cascading staircases allowed residents to safely walk down to retrieve it. These structures also functioned as passive cooling systems. As water evaporated at the bottom of the deep shaft, it created a thermal gradient. Hot desert air was pulled down, cooled, and trapped within the stone walls, creating a sanctuary for the community during extreme heat. These hydraulic systems were built with symmetry and precision, using massive pillars that doubled as structural supports to hold back the weight of the surrounding earth. Today, architects working in drought-prone areas are returning to this gravity-driven model. They are utilizing localized passive rainwater harvesting to reduce reliance on distant, energy-intensive reservoirs. The stepwell proves that infrastructure is most effective when it works with the environment, adapting to seasonal shifts rather than trying to force nature into a static state. Adapting to the environment also meant creating materials that could survive it. To achieve longevity, ancient Indian builders looked past the architecture itself, down to the microscopic level of chemistry. In the middle of the Qutub complex in Delhi sits a solid 7-meter-high shaft known as the Iron Pillar, forged roughly 1,600 years ago. By all standard measures, iron exposed to the open air and rain for 16 centuries should have disintegrated into rust, yet this pillar remains structurally intact. The ancient metallurgists achieved a specific concentration of phosphorus in the metal. When exposed to the elements, this phosphorus bonds with the iron and moisture to form a thin, self-renewing film, a shield that blocks oxygen from corroding the metal underneath. This intuitive mastery of raw materials was eventually used to produce Wootz steel, an ultra-durable alloy that dominated global trade for centuries. Modern researchers are currently studying the Delhi pillar to develop better corrosion-resistant alloys for our own bridges and buildings. It serves as a reminder that structural permanence requires a partnership with material chemistry. The urban grids of the Indus Valley, the passive cooling of the stepwells, and the corrosion-resistant iron of Delhi all share a unified engineering philosophy. These ancient builders prioritized deep observation. They analyzed their local topography, their climate, and their materials, and then they engineered solutions that worked with the environment rather than trying to pave over it. Today, we often default to brute force methods. We rely on energy-heavy cooling, chemically treated concrete, and massive diversion dams, often ignoring the durable principles that allowed these ancient sites to endure. As we face increasing pressure on our own infrastructure, we don't necessarily have to wait for a futuristic technology to solve every problem. Some of the most durable solutions for the challenges ahead are thousands of years old.